you for having me back. My name is Ravi Madduri. I work at Argonne National Laboratory in the University of Chicago. I'm a computational scientist. My work is primarily in the intersection of computing and life sciences. I I'm kind of conserving bandwidth here with multiple Zoom sessions for my kids and some Netflix going on at the home. So sorry, I don't have the video on. But it's good to see you all. I can't believe it's been a year. So primarily, I want to talk about how we've been using Parsl, and we have used Parsl quite a bit in the last year in multiple projects, and this is one of the many. MaPPeRTrac is a joint collaboration that does large-scale analysis in structural connectomes. A brief outline for my talk. I want to start with acknowledgements with the collaborators that we've been working that have been working with us in this project, and kind of give you a little bit of a refresher on why we are doing the work that we're doing, and talk how the MaPPeRTrac has evolved over the past year and a half of development, and talk a little bit about the progress that we were able to make in the last year since I presented how we kind of created MaPPeRTrac in the last presentation, and then end with some future plans as to where we're going, and hope and mention some of the issues that we kind of encountered while using Parsl, and hopefully that's just our ignorance of the amazing power that Parsl has and not being able to find it. So these are collaborators that we've been working with. So Joseph, so this project is a joint collaboration with Lawrence Livermore Laboratory and UCSF. Joseph and Timo are at Lawrence Livermore. Pratik and Eva are neuroradiologists from UCSF, and are pretty cool people to work with, and they study brains every day, and have been kind of helping us understand the scientific rationale of why we are doing what we're doing. And Mark and Alex are in my team, working primarily on making Parsl work on Amazon and Google Clouds, and working on the manuscript that we are hoping to submit soon. Okay, so why do we need? So the MaPPeRTrac is a Parsl pipeline to generate structural connectomes. Why do we need connectomes? Structural connectomes are just an important tool in a radiologist's arsenal to characterize the architecture of human brain. Our work in structural connectome is primarily focused on understanding traumatic brain injury, understanding the structural challenges or structural problems a brain can have that can predict the prognosis or diagnosis or the kind of the treatment for traumatic brain injury. This project has got a lot of connections with veterans people who fight wars and come back and have structural damage to their brain after they are closer to an explosion. So to kind of better understand what parts of the brain lead to what kind of symptoms, and overall kind of throw more light at how to treat and how to diagnose early on folks that have traumatic brain injury. It's slightly different from the functional connectome that it's a lot of people that work in that area. Pratik and his group at UCSF primarily focus on using edge density imaging. Essentially, if you think of brain as a graph, the goal of edge density is to understand how many network edges that pass through a white matter voxel inside brain. So a lot of the functional connectome focuses on the regions in the brain, the extremes, the nodes, the structural connectome looks at the sort of the edges and the path that the path that the edges are take when connecting different parts of the brain, and especially focuses on the white matter portion. The idea is that if there's a structural challenge or a structural problem in a part of the brain that has a lot of edges or connections going through it, then that may result in traumatic brain injury. That may result in a traumatic brain injury that is not immediately visible in an MRI. So this is an important piece of work in understanding human brain and understanding and getting new biomarkers for psychiatric disorders like traumatic brain injury. So just a little bit to talk about the evolution of the pipeline. So the method of generating structural connectomes using edge density imaging came out of Pratik's group at UCSF, and initially it were all like everything else in the world, I guess. The pipeline, the analysis was a bunch of bash scripts that worked really well, or worked well on one cluster at UCSF. And when this was a joint collaboration that got started with Secretary Perry interest in traumatic brain injury and helping veterans deal with TBI. So the collaboration started off with UCSF, LBL, Lawrence Livermore, and Argonne. When we started working in this, one of the first things we did was Tima worked on making it more streamlined using Python to kind of capture all of the ways that the analysis was run before. It was a lot of different ad hoc analysis that we kind of worked for some time to kind of assemble them and make them work on Livermore compute. So one of the things about this project is because it enjoyed a lot of attention from the secretary at that point, there were a lot of urgent demos that we had to run. So the Python scripts worked reasonably well to bring up results for visits, but then we had to go and make it work really well across multiple laboratories. And Parsl was a logical choice for us. So far, once we made the pipeline work through Parsl, we were able to successfully run at Argonne, Livermore, and Amazon, and currently working on getting the pipeline working on Google Cloud as well, just to kind of showcase the portability, the parameterization of the workflow, the configurability. We also have some reproducibility aspects into the pipeline where we wanted to implement some of the FAIR aspects for the analysis, and the pipeline kind of imbibe some of the ways that you can make data, or you can make research fair. So in addition to making the pipeline portable, during using Parsl and other tricks in parallelization, we were able to make the pipeline run really fast. We were able to what would take 24 to 48 hours before now takes a few hours, 4 to 5 hours for structural connectome. One of the important reasons why we wanted to work in this area is to make this pipeline work in a clinical timeline, which is an hour. So right now the work is essentially trying to figure out some of the computationally intensive parts of the pipeline, which is a segmentation, and replace that with a deep learning capability. So that's the ongoing work, and early results look like we can get the entire pipeline working under an hour, which is very well within the clinical timelines that the researchers have told us. So in the last year, we have analyzed 844 participants' brains and generated 1,239 structural connectomes. So for some patients, we have multiple MRIs during the progression of their diagnosis or their journey in the TBI. So that's why there are more connectomes than there are participants. and a lot of the compute has been done at Argonne and Livermore. Yeah, I'm almost done. So this kind of graph shows how how we were able to get the analysis done much faster. So last year we worked a little bit on making the pipeline open source. It's available in GitHub repo. So the validation verification has been a bit slower because it's all manual. So we're trying to work with UCSF to automate the validation of the connectomes that we have generated. Some of them have been validated manually, but there are a lot of connectomes to be validated. So as I said before, we are evaluating deep learning segmentation to accelerate the pipeline much more. So what's next for us? We wanted to complete the testing on Google Cloud. In addition to Singularity, we also have a Docker container. We're planning to submit the manuscript in the next couple months. And one of the issues that I found in AWS, I know that anyway, so there are some issues with AWS providers with spot instances not letting go of spot instances or reuse of the instances. One of the pet things that I always thought it would be nice to have some plugins, configuration objects that you could download that would allow for configuring and running on popular HPC compute. So that's all I had.
Cool, thank you. So we could take one question maybe if anyone has one, and if not, we can move on.
Hey Ravi, this is Kyle. So generally with these brain imaging pipelines, they're pretty computationally intensive in terms of length of time, right? So is the parallelism? You're not getting parallelism within the tools, you're getting parallelism across the samples. Is that what you're doing? And how long are these things running for? So
some steps of the pipeline we were able to exploit within the tool parallelism. So the pipeline has 5 steps, and 2 of them could be there's no data dependency between them, so we run them in parallel. Some of them are GPU based, so we get a lot of parallelism just running them on OpenMP based parallelism. So there's so right now the pipeline takes 7 hours, 6 to 7 hours, depending on the density of the MRI. It used to take 48 hours before, and with the deep learning segmentation, at least in the early results, we see that the results look comparable to the regular free server based pipeline, and the compute time is less than an hour. So it's quite interesting. But the real test is radiologists looking at it and saying, yeah, this looks good to us.
That's impressive.
Okay.
48 hours down.
Cool.
I have one other quick
No more
question.
questions. Sorry,
Whenever you're sorry, I wanted to get it in before Ben mutes me. Whenever you're running on AWS, I mean, I assume that this is pretty sensitive data. Are you how are you handling that?
So there's human connectome. They're openly available human connectome project from it's called HCP. So we're just using openly available data to run on AWS.
And then whenever you did that, are you just, I mean, is there a lot of auxiliary data that's needed, or do you just copy a input file over, run on it, and then tear down? Or
yeah.
Okay.
So there's not a lot of auxiliary files. I mean, it's just the MRIs that Human Connectome project made. I mean, they're available openly, so you just download them. So one of the things that we had to do with the pipeline is we added support for DICOM, NIFTY. I mean, so there's many formats that these data could be in, at least 3. We added support for all of those formats to the pipeline, so that you can give it any data, it will convert it into the way that the pipeline works for the subsequent steps.
Okay.